Today we're looking at graphs of rational functions. We have taken a look at these before, but we're going to get in depth a little bit more with these. So rational function, anything that we can turn into a ratio. So for instance, number one, we are looking at a rational function. That's an example of a rational function. One thing here, domain of a rational function is the set of all real numbers except the zeros in its denominator. So whenever we're looking for denominator restrictions, we've always said two things to look at would be either negatives under the square root or zeros in the denominator. Since a rational function will have a denominator, that's where you would look for your restrictions. So for number one, it's asking us to find the domain, and then we're going to use limits to describe the behavior at values not in its domain. Okay, so if we're going to find the domain, we know we cannot have the denominator equal to 0. So solving, we're going to find x cannot be negative 6. So if we were to express the domain, we would go from negative infinity to negative 6. Cannot include negative 6, so a soft bracket. And then we'd pick it up at negative 6 out to infinity. Now it wants us to use limits to describe the behavior at the values not in the domain. So if we take a look at this function, I can see at negative 6 I have a vertical asymptote. So not only are you finding domain restrictions, but that is also a way to find your vertical asymptotes. So when we use limits, we're going to approach the vertical asymptote from both the left side and the right side. So if I'm approaching this function from the left side, I can see the graph is going down towards negative infinity. The limit will not exist. Okay, limits only exist if it approaches a value. Since it keeps growing down, down, down to negative infinity, we would say the limit doesn't exist towards negative infinity. As we approach the vertical asymptote from the positive side or from the right-hand side, we can see the graph, again, it's not approaching a value, so the limit won't exist, but it won't exist towards the positive direction. So if we were to actually write this in limit notation, so I could say the limit as x approaches negative 6, now here's how we notate it, from the left or the negative side of the function. And we said it wouldn't exist, and I like to make a note and saying, well, it's going to go towards negative infinity, it goes down. As we came in from the right-hand side, so we approached negative 6 from the right or the positive side, again, it didn't exist, but if I were to look at it, it would be going up, so I could say it goes towards positive infinity. Okay? This is just going to be a little bit of a review of our horizontal and our vertical asymptotes, however, just connecting it with the limits. So for number 2, it's saying what are the horizontal and vertical asymptotes? Well, we just found from up above your vertical asymptotes. We would solve and find them the same way that we would find our domain restrictions. So I could say my vertical asymptote here is going to be at negative 6, and we saw that from the graph from before. Our horizontal asymptotes, now this is going to be a little bit of a review. This is where we had talked about our values of the exponents with our numerator versus denominator. And in this case, if I were to look at this, I could see this is like saying x to the 0. So our exponents are degree of the numerator compared to the degree of the denominator. The numerator is less than the denominator. And when that happened, we said we'd always have a horizontal asymptote of y equaling 0. And if we go back to that graph just to check and make sure, I can see, again, horizontal asymptote looking towards the ends of the graph, towards the left and the right. I can see it's trying to approach 0. Okay. I can take a look at a rational function. Notice the form that they're giving us here. It says the graph of any non-zero rational function in that form can be obtained through transformations of the reciprocal function. Keep in mind, reciprocal function, that was one of your parent functions. That's that basic 1 over x. That's what we looked at on the front with the transformation. that plus 6 just shifted it 6 units to the left. It says if the degree of the numerator is greater than or equal to the degree of the denominator, we can use division to rewrite the rational function. Okay, so we're going to take a look at these questions below, keeping that in mind. We're going to describe how this function, these functions that we have here, could be obtained from the reciprocal function. In other words, what transformations have we done to f of x to produce, in this case, g of x? So let's take a look at A just from that transformation standpoint. This could be rewritten to look something like this. Same idea, because keep in mind when you're multiplying fractions, multiply tops with tops, bottoms with bottoms, just separating it perhaps a little bit so we can see the transformations a little bit easier. So that 2 that we just factored out, that would give us a vertical stretch by 2. And if I look at the denominator, that's telling us that we're going to be going left 3 units. Okay. If we need to identify vertical and horizontal asymptotes, so our vertical asymptotes, we said, would be found from the denominator. So if I set x plus 3 equal to 0 and solve, that means my vertical asymptote would be at x equals -3. Our horizontal asymptote is found by examining our degrees of the numerator and denominator. And this is similar to the one that we had on the front. The numerator is less than the denominator, so that should tell us we have a horizontal asymptote at y equals 0. So if we were to look at this function and see what it looks like graphically, so here's our function. I can see shifted left 3 units. The vertical stretches are a little hard to see, but if we were to compare the two, you may be able to see a slight difference. You would realize it more with perhaps the algebra that would go with it. And if we were to connect limits to this, so if I were to, again, take a look at the limits approaching our vertical asymptote, as I approach it from the left, again, I see it doesn't exist. As I approach it from the right, it doesn't exist. In fact, your vertical asymptotes, when you're looking at limits, they never should exist. If for anything, it would be the direction it would go. And you can see the horizontal asymptote again as I approach the ends of the graph towards the left and the right. It is trying to get to 0. Okay, if we take a look at letter B, now letter B is slightly different because I can see my degree in the numerator and degree in the denominator are the same. Very different from the parent function. But it said we could do division to transform it. So what I'm going to do is start by doing some polynomial division, some long division. You could also do synthetic division on this case, but we'll just do long division here. So I'm going to divide through. If I find 3 times x is going to get me 3x. 3 times -2, I get a -6. And we're going to subtract everything out. So the first terms drop. -7 minus a negative, so there's plus a +6, gives me a -1. And if we rewrite this in fractional form, so now I want to think, okay, fractional form would be our answer on the top plus the remainder. So if I look at it, plus a -1, so that's -1 divided by the divisor of x minus 2. Okay, if that doesn't look right, you don't like that, here's a different way that we could write it to look like the transformation of the parent function. Okay, same thing, I'm just going to rewrite this slightly different. So now we can see some transformations that are happening here. I can see that 3, if we were to just look at the 3 is saying we are going up 3 units. This -2 is saying we are going to go right 2 units. And then this negative that we have in the front, that's saying we are reflecting over the x-axis. Okay. This also gives us a chance to look at our vertical and horizontal asymptotes. Now, I may go back to the original function to find those. If I'm looking at the original function, again, to find your vertical asymptotes, set your denominator equal to 0. So I'm going to do this over here. If I set that equal to 0, I can see that my vertical asymptote would be at 2. And now your horizontal asymptote, the degrees are equal. So if I'm thinking your horizontal asymptote, the numerator is equal to the denominator. So we said when that happens, it would be the ratio of the coefficients. So the ratio, I have a 3 on top, a 1 on the bottom, and if I were to write that, I could see that would give me an asymptote of 3. So taking a look at that on the graph itself, so I can see that I have a horizontal asymptote at y equals 3, which should also make sense because we just shifted that parent function, we said up 3 units. So where the parent function would have a horizontal asymptote at 0, if I shift 0 up 3 units, that gives me that y equals 3 horizontal asymptote. Vertical asymptote we can see happening at positive 2. And again, if I'm shifting it to the right 2 units, I should see from my normal parent function, again, that should kind of check out if we're thinking about this in terms of transformations. Okay. Taking a look at another problem. So again, we're finding the horizontal and vertical asymptotes, and then we'll talk about this from a limit perspective. So if we start with the horizontal asymptote, similar to the last problem that we did, I can see the degree of the numerator is equal to the degree of the denominator, which means I will take the ratio of their coefficients. So I have a 1 on top, a 1 on the bottom, so that tells me I have a horizontal asymptote of 1. Your vertical asymptotes, we take our denominator, set that equal to 0, and solve. So if we were to solve this, I have x squared equals negative 1. But when you try and solve, we have a square root of a negative 1, which gives us an imaginary number. So if I have an imaginary number, this is saying you have no asymptotes. Okay, or at least in this case, no vertical asymptotes, since that's what we're trying to find. And if we take a look at this graph, just to compare and make sure that this makes sense. So here's our graph. There are no vertical asymptotes, there's no domain restrictions. And if I look at my horizontal, I can see as I approach the left and as I approach the right, it's trying to get to positive 1 on both of those. And that's what we found, since the ratio of the coefficients would give us 1. And our last example here. We're going to take a look at, well, what happens if the, in this case, numerator degree is greater than the denominator. So we're trying to find the asymptotes and intercepts. So let's work with the asymptotes first. Let's do vertical, because we know how to do the vertical. We know how to do both, but this one's going to be a little bit easier, a little bit more straightforward. Set your denominator equal to 0 and solve. So I'd have x squared is equal to 9. And if I solve for x, I need to square root both sides. And that would give me x equaling both positive and negative 3. So this one says I have 2 vertical asymptotes. To find your horizontal asymptotes, again, we're going to examine both the numerator and the denominator's degrees. And in this case, I see the numerator is greater than the denominator. So we would always say in this case then, well, then there's no horizontal asymptote, which is still the case. However, what you get is a slant asymptote. So when you have no horizontal asymptote, you're going to want to check for the slant asymptote. And how we do that is by doing some division, some long division. So if we do some long division here, I have x squared minus 9, and I'm dividing through by, or dividing it by x cubed. I said that backwards. X cubed divided by x squared minus 9. Now, we may need some placeholders here, so you could fill them in to begin with. So we have 0x squared plus 0x plus 0. Not a bad idea to fill them in just to kind of keep things in order. And if I multiply through and I say x squared times x would give me x cubed. So there's my x cubed. X squared times negative 9, that's going to get me a negative 9x. And keep in mind we're subtracting. So when we subtract, that first term drops out. I have 0x squared, so still 0x squared. 0 minus a negative 9x is going to give me a positive 9x. And I have a 0 for a constant. So if I were to look at this function and I were to, again, rewrite this in fractional form, this would give me the answer of x plus, our remainder here would be 9x divided by the divisor of x squared minus 9. So that's just writing the answer in fractional form, maybe looking at it in a different form. But now where in the heck is the slant asymptote coming from? Well, your slant asymptote comes from what you get from when you divide. All right, so I could say here your slant asymptote is going to be the equation y equals x. They also wanted us to find intercepts. So again, maybe a little bit more of a review for intercepts, but let's try this again. If we're going to find a y-intercept, we want to think make x equal to 0. So anywhere I see an x, I'm going to make it 0. So that would give me 0 cubed over 0 squared minus 9. And when I solve, this is going to give me 0. So I can say my y-intercept is located at the coordinate 0, 0. Your x-intercept, we want to think make y equal to 0. Well, that's like saying take the entire function and make it 0. So how does a fraction become 0? You have to think about that. Well, your fraction becomes 0 when your numerator is 0. So to solve for that, all I have to really do is think, okay, make x cubed equal to 0. And what we're going to find when we simplify is 0 cubed is 0. So what is that telling me? That's telling me my x-intercept then is going to be located at, still again, 0, 0. So we have found all of those. Let's go and take a look at the graph. And here's our function. So we said that we would have, for a vertical asymptote, a positive 3 and a negative 3, and we can take a look at the graph, see it's approaching there. We said no horizontal asymptote. We did say that we would have perhaps I take a look at your x-intercept and your y-intercept. I can see that we have it crossing at 0, 0, and that would be the only point that it intersects the axis. So your x-intercept and your y-intercept, they fall at the same location. So I hope this helped, and if you have any questions, please come see me. We will practice this a little bit more in class, and I hope you like and subscribe. Have a great day.